Welcome to our seventh lecture on solar electric power systems. Today we will talk about market development of PV, including off-grid markets, markets triggered by feed-in tariff, self-sustainable markets, cost and price development. Also we have an extensive exercise to that because there's a public holidays next Monday, and so you will be able to prepare that at home on your own. So this is a global perspective on the development on the renewables. This is the upper blue line. So you see here most of the new installed power plants are now renewables with a quote of 63%. Starting 2008 on this graph with 93% only. So it means if you include all kinds of power plants, not only renewables, but any kind of nuclear, coal power plants, 63% are renewables, mostly hydro. Renewable power as a percentage of global capacity, it's still not that high because we have to wait for some years, but it's rose to 33% of the global capacity. Then we have the generation. It's a bit lower. It's 26% only. This depends on the kind of generation you have. This is a capacity factor. Some renewables is quite high. Speaking about hydropower or geothermal energy, while it's a bit significantly lower at the wind and solar power, depending also on the location of installation. The lowest line is the yellow line. This is as a solar power as a percentage of global power generation. So this 2.2% 2018 is solar photovoltaic power. Last year, let's say almost 2 years ago, 2018, the global installed capacity was in solar 1,002 gigawatt of new solar have been installed, followed by wind 49 gigawatt, almost the same level, coal 50 gigawatt, 46 gigawatt in natural gas power plants. Nuclear only 5 gigawatt. Okay, you have to consider that it's running through the whole year, but still if you compare 5 gigawatt to 102 gigawatt, it's clear that the preference here was on solar. Also last letter I told that still the largest, but in terms of generated energy, but only third place in installed capacity of renewables, and this due to the high capacity factor. Here you see the development of photovoltaics, including the regional share. So it's first started with renewable energy legislation in Germany. It looks very small there, but during that time, the year 2000, it was quite, I think from the year 2000 until 2008 or so, Germany was about half of the world photovoltaic installations. Yes, then it took off. Europe stalled a bit. It was not only Germany then, it was Spain in 2004, and a lot of have been installed in Italy too. And then China took over. If you see the installation numbers after 2014, 2015, you saw before half of the work, obviously later, here half of the work market is occurs in China. If we go back to that, altogether we have installed capacity of about half a terawatt, 509 gigawatt of installed power with index P. That means under standard test conditions. So the was followed then by US, very close to India, with each of 9.6 gigawatt in India, and United States about 10 gigawatt the market. Then Japan in Unfortunately, Germany was not happening so much as it's been before, but still, if you see the numbers here, 2018, almost 3 gigawatts have been installed. But in order to reach a sustainable energy supply, it should be much, much more. Otherwise, we have to wait for centuries until all conventional power capacity is substituted by photovoltaics. Here you see the relative share of segments inside Europe. So you see the yellow part is the utility scale, so large scale power plants of photovoltaics. Then you see the industrial installation and commercial installation in light and middle blue. And in dark blue you see the residential installations on private rooftops and so on. So here if you go to the first example, that's Romania, you see it's almost entirely on utility scale, only very small, a small part in residential scale. If you go to the other side, you have Slovenia, where you almost haven't any utility scale photovoltaics, but mostly a commercial and some part in residential. If you take a look at Germany here, it's split up, not equal, but almost equal shares. We have here a share with utility scale of photovoltaics. We have a share of large scale of commercial scale and industrial scale, and some considerable share in residential scale. Here you see the price development and learning curve of photovoltaic module. Please take into consideration this is a logarithmic curve on both sides, so y-axis and x-axis are logarithmic. You see here the price developments in the 80s. You saw here this is 10, 20, about 30 euro per watt has been the cost, and then this is accumulated installed capacity. That means the more you install, the cheaper the price gets. So this learning curve is about a 24% of price reduction by doubling the installed capacity. So you see that distances between the years is different. This depends how much happened during this year. So for example, if you take 2000 until 2010, you see a large improvement in cumulated active installed capacity, but also in price reduction accordingly. That means this was due to the feed-in legislation. It took off really well, and a large number of photovoltaic power plants have been installed, and due to that price reduction occurred. Not as much as expected in 2010 because there was a kind of scarce of photovoltaic modules, so prices have been a bit elevated. But then after 2012 or so, price were a bit lower than that curve. I mean, there was a bit overproduction and prices were a bit lower than expected. Here we come to 2018, prices are in the vicinity of 30 cents per watt peak. So nobody expected that before. It's, if you see there's a factor of 100, it got cheaper. This doesn't happen at any energy technology. These are the final prices. These have been the production prices, and these are costs for the end consumer. Here you see end consumer 2006 when he bought a residential system. He paid about 4,700 euro per kilowatt peak, or 4.7 euro per watt peak, and most of it, 71%, had been for the cost of the modules, and 29% for the balance of system costs, including inverters, we discussed in the lectures before. Due to the rapidly sinking prices of photovoltaic modules, this changed a bit. So nowadays, not the photovoltaic modules are the most important item for a photovoltaic system. It's BOS costs. So you see, it makes much more sense in looking how to save a BOS cost rather than the modules, because the competition is really high and prices are really low. But here at BOS, I think there is room for improvement. You see, in total, the prices are in the vicinity of 1,200 euro per kilowatt peak. So this was a considerable risk reduction. Not as much for the solar cells and the module alone, but still a good reduction for the end consumer. And if you take a look in the year 2000, this was a graph set up in the year 2000. This has been the expectation for 2020, what we have today. So in the year 2000, 4 locations as Germany, where we have about 900 sunshine hours per year or 900 full load hours per year. Prices have been in the vicinity of 60 euro cent per generated kilowatt hour. And if you went to sunny locations, to southern Italy, to southern Spain or northern Africa, this is equivalent to 1,800 full load hours of the PV generator, and this was equivalent to 30 euro cent per kilowatt hour. Then it was expected that until the year 2000, prices of generated electricity would go down to a bit more than 20 cents per kilowatt hour, and for the sunny locations to about half of it, to about 10 euro cent per kilowatt hour. But interestingly, usually these scenarios are quite optimistic, but these have been too pessimistic. Actually, the prices went down even more. So we reached the 2020 value almost 10 years ahead. So if you take a look at, for example, 2015, we already reached for locations in Germany the price which was expected for Spain in 2020. And if you went down to southerly locations, prices was really only a tenth of the price of the year 2000, about 6 cents per kilowatt hour. And for the year 2020, yes, we have a latest price about 5 cents for kilowatt hour in Germany, according to the latest tenders. And latest prices in the Emirates have been even 1.5 cents per kilowatt hour. So if you take into consideration the electricity cost versus the feed-in tariffs, so these lines represent the money you get by this prime tariff in about the year 2000. It was a bit more than 50 cents per kilowatt hour, and this was differentiated then between this is the average tariff, is considering the old tariff, so this is a bit above, so this also has a burden from the older installations. And in green we have the price development of ground-mounted roof-mounted, so this was differentiated between residential and roof-mounted system, which received a lower compensation then. And in the year about 2011, then we reached so-called grid parity. So the prices and the compensation for the feed-in of photovoltaics has been about the same price as the electricity price. So in the vicinity of 22 cents per kilowatt hour. And nowadays we are in the favorable position that photovoltaic electricity prices and also the compensation is lower than the prices from electricity. So it makes the prices from electricity from the utility. So it makes completely sense if you have a photovoltaic power plant at home, not to wait for compensation, but to substitute your own electricity at home, while this you get 30 cents, or you can compensate for 30 cents, and you only get 10 cents from the utility for feeding in. This graph shows on one side the levelized cost of electricity, and the base is the total cost of our plant for 3 locations in Germany. For example, if we take Paderborn, unfortunately sun is not very good there, so we have irradiance value of 950 kilowatt hour of irradiance per square meter per year. This you know from the first lecture. And if you achieve to install your PV power plant, for example, for 1.1 euro per watt peak, you arrive at a price in the vicinity of 9.5 euro cent per kilowatt hour. If you would install the same power plant in the sunniest location of Germany, that is Freiburg, southern Germany, then you should follow the red line, and there you have a price which is below, a little bit below 8 cents per kilowatt hour, and this is about 7.9 cents per kilowatt hour. And this is equivalent here to a irradiance value of 1,160 kilowatt hour per square meter per year. Here the dashed lines, the gray dashed lines are the remuneration. So you see here the line is the remuneration for a small roof here, and you see here in Paderborn, if you achieve to install system on your home, including everything, installation, POS costs and modules, for about 1.4 euro per watt peak, you can still make some profit, because the compensation is about 12.5 cents. You have production costs of about 12 cents per kilowatt hour, so profit is really small. If you install the same power plant in Freiburg, for example, you will be able to produce solar electricity for about 10 cents per kilowatt hour. So you have a large, quite a large profit. So from 10 to 11.5 to 12.5 cent or so. This is a nice graph. It has to be updated. It's 2017. I didn't find an updated version. Perhaps you have to do it on your own. But I just want to show you the principle, how this is done. So you are able to see whether very quickly whether a project can be profitable if you have the remuneration price. The problems during the last years had been that the remuneration price has been bouncing a lot, so there were some revisions every couple of months, and then there was a threshold with 52 gigawatts, and nobody knows when the threshold after 52 gigawatts will be reached, whether there still will be any remuneration at all. And so the installations during the last couple of years haven't been haven't been a lot. It should be much more if you consider the prices for the PV models. Here you see the global prices here for any kind of electricity provider. So you see here the solar line is just, it started in the year 2009 here with $350 per US dollar per megawatt hour. That is about equivalent to about 30 euro cents per kilowatt hour, and it went down. You saw before the last tenders in Germany had been in the vicinity of 5 cents per kilowatt hour, and if you go to really very sunny locations, for example in the Emirates or even southern Portugal, there the last tenders were sold for 1.5 cents per kilowatt hour. And you see here, that's here you see the conventional energy sources, here nuclear in the gray line. So it didn't achieve to reduce the prices, and contrarily it even increased the prices, so we are in the vicinity of 10-15 cents per kilowatt hour nowadays. And coal about the same, and it will be even worse, because we have to consider then carbon dioxide price, which is steadily increasing. Wind power also, the renewables got some price decrease, but certainly not as much as photovoltaics. The combined gas power plants, they also sank a little bit in price, but are now higher than photovoltaics and wind. So here you see some power purchase agreement prices, what's been happening. First we have in the years 2012 to 2016, the wind power purchase agreements have been constantly lower than the power purchase agreements for solar. So you see here, started in 2012 in South Africa, the lowest tender have been here at about 78 US dollar per megawatt hour. In Jordan, solar was about 12 cent per kilowatt hour, or 12 US cent per kilowatt hour. And here you see the latest prices here to 2016. If you have newer prices, now it should update this. It's told you it's 1.5 euro cent here in the Emirates in 2020. And Germany now was the last tender about 5 euro cent per kilowatt hour, even going down to 4 euro cent per kilowatt hour. It's not only the electricity price plays a role, it's also, or the electricity prices are not defined only by the cost of the equipment. They are also a function of the cost of financing. And here you see some different scenarios for financing costs of 3%. You see prices here for residential PV worldwide. In Germany it's a bit cheaper because they have got a lot of experience in that, and commercial PV is in the vicinity of 10 euro cent. This is still at 15 euro cent. And if you have financing costs of 7%, it goes up to 200 US dollar per megawatt hour, or about 20 cents per kilowatt hour. And if you have 10 cents, that's absolutely deadly. So the competitiveness of photovoltaics is steadily decreased. So low interest rates are really important. So these are later, this is 2018. You see here that here the auction prices here lowest in 2018 was 1.86 euro cent per kilowatt hour in India. As I told, now we are in the vicinity of 1.5 cent per kilowatt hour. This is a new scenario that you don't get any compensation anymore at a fixed rate. The new scenario planned by the Ministry of Energy is that you have to compete on the free market, and this is done accordingly to the merit order methods. This is carried out at conventional power plants. Here you see an example of 2018. And what is done, you have the load requirements. For example, you need 50 gigawatts for the next day. Because expectation for the load and minus the load minus the production of wind and solar. The remaining will be 50 gigawatt. And then you purchase that electricity in advance. So you start with the cheapest. That's quite natural. So this would be waste energy. This costs nothing almost. And nuclear energy is also cheap because it's kind of subvention, because they don't have to bury the costs and so on. So these are quite cheap, but this is limited after 11 gigawatt. Then the next cheapest is night power plants. They are in the vicinity of 2 cents per kilowatt hour. Then the next option is hard coal. This will be this option. We go to 50 gigawatts. So this is the price then we have to pay for our most expensive slice of electricity, which is in the vicinity of 38 euro per megawatt hour, or 38 cents per kilowatt hour. And if you have a really high power requirement at night without any wind and so on, and this goes up, sure you have to pay more. The gas turbines have many advantages. They are the carbon dioxide production is only half compared to coal, and also they are very flexible, so you can quickly adapt to changing conditions. But as you see here, the prices are quite elevated, almost double as some lignite power plants. Mineral oil is the most expensive. If you go to Africa, you see that a lot of the energy production is done with these diesel power plants, but they are far the most expensive one. And unfortunately, that poor countries, they have to the most expensive electricity production. But it's good news for photovoltaics because you can easily compete with them. As I told, if you go to Africa, you will have electricity prices in the vicinity of 20 euro cent per kilowatt hour for large scale, or perhaps 40 for 4 cents per kilowatt hour in even if you have residential systems, depending on the import costs or something like this. But if you see the pure material costs or the pure equipment costs, that's feasible. This has been calculated for CO2 certificate of 18 euro per ton in 2018. Nowadays it's in the vicinity of 25 euro per liter, and so these prices are a bit more elevated nowadays. These are the expectations for the next years. So you see here some prospects about the photovoltaics. So you see here that China will have quite sunny prospects still, so as many other countries. Japan, a bit some cloudy things. Nothing to do that the sun is not shining anymore, but the problem is the grid capacity is not sufficient, and it cannot sell anything to neighboring countries because there is no wire to the neighboring countries. And also they have they have two frequency systems. So in the north is a 60 hertz system, and the south is 50 hertz. And so they cannot distribute evenly the generated PV power. So they have to convert it first to the according to the adequate frequency there. So this is a bit more difficulty. So the growth will be a bit limited. But in general, they have an installed power now of 63 gigawatts. That's quite considerable. And so you see here that here some Turkey, for example, this is which rain they stopped apparently the program for photovoltaics, but many other countries running really well. Here, for example, Egypt, you have a growth rate of 50%. So this really, really impressive. Or United Arab Emirates, and therefore also the price went down significantly, as I told you, so in the vicinity of 1.2 or 1.5 cent per kilowatt hour. So this is also the prospect, what will be installed in the future. This always changes, so this is just take a look in the glass globe, what will happen there, and so this is expected. But they're really good. So this is photovoltaics always getting cheaper, and as you saw, conventional energy sources get more expensive, and so it's competitive even with storage and so on. Before it was the excuse by the utilities which deliver only conventional energy. So they said, okay, you have solar, it's very cheap during daytime, but not during nighttime, and so we have to consider storage. But also storage is getting really cheap, and we discussed this in a follow-up lecture about the storage development, and then you will see that even with storage, photovoltaic is becoming competitive. So here you see the different scenarios. So the low scenario rooftop will be 44 gigawatt installation 2023, and at the high scenario even almost double, 76.5 gigawatts. For utility scale, it's even more. So you have here 187 gigawatts that will be installed in 2023. If you consider high scenario and low scenario, 81.7 gigawatt. So in the future, that will not be only a so-called prime tariff. There will be also a kind of business models, so-called prosumer business models. So one is optimizing self-consumption rates without using the public grid. So use electricity you generated on your own at home, and you have your own storage and energy management system. The abbreviation is EMS. You have a collective self-consumption optimized with storage and EMS in a building. Or you have a microgrid with solar storage and EMS. So this goes up just from your household to a whole building and to a microgrid which can consist of a small city or at least of many buildings. Yes, and then optimizing local self-consumption rates, but using then the public grid. So you can have collective self-consumption with solar and EMS at neighborhood level. So you can, for example, you go on holidays in summer and your photovoltaic power plant is still producing. So instead of selling it to the utility, you may sell it to your neighbor, kind of a peer-to-peer business. And that's usually more profitable because your neighbor usually has to pay about 30 cents per kilowatt hour. And if you have a feed-in tariff, you have only get about 10 or 9 cents per kilowatt hour. So it's more profitable maybe to sell it for 20 cents for your neighbor. So you make a lot of money and your neighbor is saving a lot of money. This is peer-to-peer trading, as I mentioned. And also what you can do is providing a system flexibility. So you have storage and you will use your storage when electricity is more expensive on the market, and you will store when you don't get a lot of money on the electricity market, but that requires dynamic tariffs. If you connect a lot of power plants together, storage and your PV and maybe wind power plants, you can set up a so-called virtual power plant, which is able to work 24 hours a day for 365 days a year, and usually you get a much better tariff if you can supply a steady load. This is also in the discussion now that you get a compensation rate in the future of 8 cents for such a steady generation. It's fixed yet, but in the political network they told me that this is really be the future. So there's not anymore you just generate photovoltaic energy during midday only and nothing at night and get some compensation for it, but to really operate on a system level and generate steady power, or at least considering considering the load curve. Here's the outlook of installed PV capacity. As I told you, we have about now half a terawatt of installed power, and that expectation that until the year 2023 we will get, even if in a low scenario, about 1 terawatt of installed photovoltaic power under standard test conditions, or at a high scenario 1.6 terawatt installed power. And in the exercise we will calculate with such growth rates, find out the growth rates, and then calculate, for example, how many years we have to wait with current growth rate until we can supply the whole planet with photovoltaic electricity. Well, there's been often in discussion that photovoltaics is very expensive, so it increases a lot the electricity price in Germany. This was true for the early years here because the compensation price have been really high, as you saw in the vicinity of 50 cents per kilowatt hour, while you have nowadays for large scale you have only 5 cents per kilowatt hour. So for each new power plant being installed, the growth of electricity price is not very high anymore. So this is mentioned here. So each new gigawatt of photovoltaic price increases the compensation costs, so the EEG-Umlage, by 0.018 cent per kilowatt only. So very little compared to the early ages. Just as a reminder, the compensation rates are not sponsored by the government. It's no subsidy. They are paid by the electricity consumer. So the additional costs they are paid by the electricity bills of the final consumer. And so you have here the prices for photovoltaics in comparison to the prices on the market, and the difference between that has to be paid. This is getting smaller and smaller, so the compensation is getting also smaller and smaller. A bit of problem occurs while we have overproduction. Then at overproduction price, for example, due to inflexible lignite or nuclear power plants, the price difference is increasing. Not while photovoltaic is getting more expensive, but while we have sometimes zero price or negative prices due to the overproduction. Some people even say that's on purpose to increase the price difference to make photovoltaic more expensive. Sometimes it really seems like that, but we don't have any proof for that to showing that. But there's a big political discussion because these early years they cost a lot for the electricity bills, and this made household electricity in Germany quite expensive. Here you see a load curve. So this is a typical load curve in Germany. So you have here the peak load about midday, and this was very profitable for the utilities. They can switch on their peak load power plant because electricity was quite expensive during that time. In the nighttime, electricity have been quite cheap. These are the so-called baseload power plants. For example, lignite and nuclear power plants. They don't have any good throttle capabilities, so they constructed decades ago to be run 24 hours for 365 days a year at a very cheap price only. Nowadays, you have to think about increasing the flexibility. As you see here, for example, if the sun is shining, here is a clear day power output. So you see here this peak load is significantly reduced or even put to zero during the midday hours, and but also has impacts to other parts of the day, even attacking base loads. For example, if you consider wind power also, this is not considered in this picture. So on the other hand, you have days like this, a gray zone here. This is PV power output during a dark gray day. So very little, and then you don't compensate any at all. But you should have this reserve then, either by, as I mentioned, this so-called virtual power plant. So you combine many power plants together with our own storage, or via backup power plants in the grids, which are able to cope with the high fluctuation. Here's some examples here. So you see here the 2017, I just opened the browser so you can read some actual values of very recent values. So this is for some days here. You see here the gray part is the conventional power plant, so nuclear and coal and lignite power plants. And here you see the solar part here mainly during midday. And here you see the prices. And you see here they're clearly negative prices during midday, because usually the consumption stays about the same, but then also the generation of conventional power plants should throttle down, and in 2017 they were not able to do that, and this caused negative prices. It's still the case, but according to many utilities and many operators of coal power plants, they are more flexible than it has been some years before. Here in the light green or greenish color, this is the wind power. So you see here the wind power here in this day, so it caused even negative prices during the nighttime, not only during daytime. So here we would have a large share of solar and wind power during this part, and so there should be a more severe throttling of nuclear and coal power plants during these periods. Here you see the different power plants here. As you see here, the only plants which have been a little bit flexible here have been here the hard coal power plant. They are a bit flexible, as you see here. The lignite power plants haven't been any flexible at all. So do the nuclear power plants here in the red color. So even if you have a kind of overproduction, there was no throttling. This This is hydropower, not stored hydropower, but river hydropower, so they're not able to really throttle a lot. They can only bypass the water, so on. And the green one is a biomass power plant. I was wondering because theoretically they would be able to throttle, but apparently it's not really a problem of the actual generation. It's a problem of the monitoring, because there are many farms there and they don't have an accurate monitoring. They only have a meter for a month, and they don't have any hourly recording of their power production, and so this you see is probably wrong. There is some fluctuation here according to the power requirements, similar to the one from hard coal production. So you see, if you click on that, you can see some the actual production for many things. As you see here, the total power was 81.59 gigawatts, and solar had a large share, 28.61 gigawatt, and wind was not windy, it was 3.37 gigawatts and so on. And you can do this also for nowadays. This was here which a large share of power. So here you see this is not this one before has been by energy-charts.de, and they give the presentation. This is operated by the Fraunhofer Institute Eise in Freiburg, and this is by Agora Energiewende. This instrument is called Agorameter. Just type in Google Agorameter and you come to this site. And I like this quite a lot. I like both a lot. But here you see the consumption curve also. So you see here the total production was significantly over the consumption. So this has to be exploited even at a very low price and even at negative prices. Here you see, for example, that it's 30.7 gigawatt of production during midday. There's also another instrument by SMA. It was even online, so you could really follow up per minute what's the actual production. Unfortunately, this is not the case anymore. You have a delay of about 3 hours to really see what has been happening before. Only if you pay a lot of money for getting direct online access, you are able to follow this directly. So this is Germany. This was a very clear day in Germany. You see about almost 100% is some sunshine. So even only some the Saarland is, and here I think it is Bremen or something like this, received a bit less sunshine. On altogether, power production was about 24.7 gigawatt during that time. And what you see here that there is sometimes so this was the misinterpretation of the actual production. So the prediction of the actual power plays a really important role on the market. So the more you are able to predict the actual power production, the more accurate works the system, and the less prices have to be paid by the final customer. If you split up the electricity bill, the share of energy production is not any more expensive, because you have really cheap solar production, but the cost of energy management and the grid is now more than the cost for the actual generation of electricity. We come also to this a bit later. This is new idea, just as I mentioned, also peer-to-peer dealing with PV electricity. I called it during that time PV 3.0, and this means that you have free access to grid and control power market, and this will be equal to the so-called prosumer model I've been explaining before. When I just set it up first here, there was no this prosumer hardly existed this word, and so this was my idea, called it PV 3.0. I think it was 2012 or 2013, and the idea was pretty much the same. So you have your own electricity, your own auto consumption, or you can go on the market, especially if you are on holiday, you can sell it on a kind of pop marketplaces. I call it eBay of energy, and or you can make a direct power purchase agreement with your neighbor, and sell him your PV electricity for 3 weeks or so, as long as you're on holiday. Or you can buy it via the public marketplace. Usually perhaps you have to pay some fees. Usually direct PPA is more favorable for both sides. Then you even can make not only an electricity provider but also a storage provider. So you just have stored electricity and sell it and buy it on the electricity market. Usually you buy it when it's cheap and sell it when it's more expensive. And this is for long-term stored energy, and control power is usually for short-term stored energy. So you can make it available quickly. You can achieve a quite high price. For the operator of a PV power plant without storage, as I mentioned already, the feed-in rates are quite low, so you cannot make really a lot of money by that. Here are some, what I mentioned before, fast throttling capability of conventional power plants is a must. So you see here the export here. This is quite good in Germany. They have a lot of neighboring countries, so they can sell some electricity. Even for storage, for example, there's a lot of hydro storage power plants in Austria, in Switzerland, or very large capacities are in Norway. The first line is finished already, and it will go into operation this year already. The Netherlands have that about since 10 years, since 2008, so 12 years already. Also Denmark is one, and Denmark has a lot of wind power, and so they store their wind electricity in Norway. But you see the same issue here. If you take a look, this is I think 2013, and you see a lot of solar power available and a lot of energy being exported, and this has an impact on the electricity prices. So here you see the electricity price in blue color. And when sun is going up then, and that's reduced power, then price is quite high. In the midday, price is lowest. In the evening hours, then electricity trade price goes up again. How to avoid that? Because it's a problem for the final consumer, because they have to pay the difference costs, is, for example, to install east-west orientated photovoltaic power plants instead of strictly south orientated PV modules. So this is shown here. So this is a traditional way how to install PV power plants strictly orientated to the south direction, and the east-west orientation. As you already saw, I think at the Grinner video, when they installed the 300 megawatt power plant in France, this was also already in the east-west orientation. So you lose some kind of energy production during the year, but on the other hand, the electricity production during each day is much more equilibrated, and on a system level it's much more favorable. And according to Grinner, it's even more favorable from a construction point of view, because the attack angle from wind, for example, here from north is much less, so it's much smoother in the wind, and so the layout of the civil engineering can be reduced, and the requirements and the costs and so on, and so the little reduction in yield can be easily be compensated by the less civil engineering work that has to be done. And if you come to an agreement with a utility, you can even negotiate that if you're producing electricity more on more equilibrated during the day, that you may get a better price rather than you only produce it in a fixed southerly tilt angle. But you have to really have a big power plant in order to do that. If you are a small residential power plant, I think the utility doesn't want to speak with you. For them it's too much bureaucracy and so on to make extra power purchase agreement. But for large power plants, that's feasible. Or you can come up with a project with many citizens together. This is called citizen energy, and then set up together a large power plant, and then it's more easy to negotiate with a large utility. Here you see the effects of such a system. So the traditional power photovoltaic energy system is in blue here. So you have a strictly south orientated maximum at midday, And in the red you have a southeast orientated PV power plant here. Maximum is at 920 in the morning. You see that the maximum isn't as high as on midday, so you will have some some losses in yield, and about equivalent to the evening. So you have the maximum if you orientate it with the azimuth of 225 degrees. That's equivalent to southwest orientation. You have your maximum at 2 o'clock and 40 minutes at 2 p.m. 40, and so then the total yield will be a bit less. But as you see here, if you combine that, the green and the red line together, you have over the day a much smoother energy delivery. Also, you can think about not only changing the azimuth, but also the elevation angle. This is a rather this is a scenario with large photovoltaic installation in Germany. So now we have about 50 gigawatt, but this is for the future with 400 gigawatt if you want to really go towards 100% renewables in Germany. Actually, it sounds a bit really, so we go only about fourfold and eightfold, but the prices went so low, as you saw, so it won't cost much more as the first 50 gigawatt we installed, the additional 350 gigawatts to reach 400 gigawatts. And here you see the traditional installation at an elevation angle of 40 degrees. So this is a month, so in January and February electricity production is rather low, and then it goes up, and then you have a lot of production of about 50 terawatt hours per month in June, July, or even in May. It's like this, and then it's going down. And here in the gray line is the electricity consumption, and it's okay in summer, so we will have a large overproduction here during that time. So it only fits in mid of March, and in about September, end of August, this both curves meet each other. So the consumption is exactly the same as the generation by photovoltaic electricity, and in order to equilibrate that a bit, or equalize that a bit, we use here a 60 degree of elevation angles for the PV power plant. That means we have some reduction in summer, so it fits better to the actual consumption, and some increase in the early in the first month, January and February, same as in November, December. It doesn't look like a lot here. But it's actually 12-14% more, and you save that in additional power plants or backup systems. Here I made this, here to explain it a bit. So if you have zero elevation angle, that means a horizontal, for example, if you put it flat on a lake or something like this, then you see that the different relative yields. For example, if we start in July with 1, then we go to the different elevation angles. So if you increase a bit, you have a bit more, but if you increase it to 60 degrees elevation angles, you will lose in July. But if you incline more in January, you see they have a significant increase from 0 degrees to 60 degrees. You double your electricity production just by the module elevation angle. We didn't discuss 0 degrees on this graph. This was only between 60 and 30 degrees, but you still see there's a significant increase from that number to that relative number in terms of additional energy yield. And it looks a little, but it's actually quite a lot, and you can save some. So these are some methods how to really think forward a bit, not only to maximize energy production during a day, but think about the energy system and for the whole year. This shows the new trend in Germany, the home storage. So first, this is without PV, and if you would use your PV directly at your home, you would be able to reduce your consumption by about 30%, because some of electricity, if you don't have a storage, you need to power your light at nighttime or your TV at nighttime. So this is remaining 70% you have to still purchase from the electricity grids, while here, if you have a storage, you are able to cover the main part by your own solar PV system. This depends on size and so on, and the size of the PV power plant, your consumption profile, and your storage. And this was just calculated for a typical household with 4 persons, yearly consumption of 4,500 kilowatt hours per year, and a PV generator of 5 kilowatt under standard test conditions, and an effective storage capacity of 4 kilowatt hour. So if you have a bigger storage, you can even reach 100% autonomy if you increase the size of the storage and the PV power plant. We come to this later then. If you have such a storage, you can also think about to do something for the system. So this is a more egoistic regime for operating your battery. So you just, as soon as some light is available in the morning, you start charging your battery, because you used it during the nighttime, so it's half empty or so, and you immediately charge it, and then it's full about 10 o'clock or 11 o'clock, and then you feed the rest of electricity into the grid. That's not very favorable, because the dynamic for the grid is really high. So there's zero electricity delivered to the grid, and then there's a peak delivery at midday, and the grid has to digest it. So you have to have additional power plant, which are really expensive, and also the dynamics of the remaining energy system has to be able to cope with that. And then, yes, if batteries are full already at 11 o'clock in the nighttime, you can use it up. A more favorable regime for the operation of the battery would be like this. So you start immediately when sun goes up to feed into the grid, not charge your battery. You feed into the grid, and at 9 o'clock or so, you start charging your battery until 4 o'clock or 3 o'clock in the afternoon. And due to that, you have about 6 hours of charging. That's usually sufficient to charge to fully charge your battery, especially while you have here peak generation during that time. And for electricity, you have the electricity grid. It has to digest a much lower peak load, and also it gets electricity during the morning hours and during the evening hours. And that's more favorable, and should also be compensated at a much better rate, because you're doing something for the infrastructure, and the infrastructure investment costs, which are really high at the moment, because everything is designed for the peak load. They can reduce the maximum transportation capability of the grid, also for the dynamics of the remaining power system. This is some outlook for the new markets. Diesel power plants here, the tiny of their diesel power plant installed worldwide with power of 500 gigawatt. So it's equivalent to the installed PV power we have nowadays. This is mainly here what you see in sub-Saharan Africa. So here more than 50% of the countries are powered by diesel power plant. And you saw the merit order graph. This is a really expensive way of producing electricity, and these are the markets where you can easily substitute it by photovoltaics. So this is a scenario. It's a bit older, and now it's even more favorable, from 2012 here by my colleague Bayer. Here, for example, he made a scenario. You can also look up on his website. He's just updating this constantly, but just to give you a scenario here at a certain point in time. So you have here the red part. So here photovoltaic isn't competitive because the conventional electricity is too cheap. So this is basically here for the Arab countries or Iran and Northern Africa. So photovoltaic isn't competitive there then, and also for Greenland because they are subsidized, and also the radiation is very low. Some countries here, Venezuela, sure, electricity is, diesel is very, very cheap there, and some other countries. But most of the world here you see photovoltaic was already competitive during that time, the 2012, all the green and the yellow parts, and you can easily substitute the energy generation there by photovoltaics. You saw here, this is a graph you saw, it's just photovoltaic is really one of the cheapest sources of energy. Here, this is an update since 2011 where this was made, or 2012, from 14 to 4 cents per kilowatt hour. So this was here, the threshold was made at 14 or 15 cent per kilowatt hour threshold for being this is already to be competitive. Now you can move this green arrow more up, and just already half of this of the red part is already competitive. Here's also a graph. This is just highly dependent on the fuel price. So even during the last weeks it changed dramatically, but this is just to show you an example how the method is applied. So you have here the average cost of electricity generation in euro per kilowatt hour. This is here the y-axis, the annual irradiance on a module in kilowatt hour per square meter per year. So it's Paderborn in this vicinity 950, a bit off the scale here, 950 kilowatt hour per square meter per year. And if you're able to install your PV system at a price of €1 per watt peak, you will be able to generate electricity for 10 cents per kilowatt hour. If it costs more price, for example, €1.5 per kilowatt hour per watt peak installation costs, photovoltaic panels plus BOS costs, you arrive at 15 cents per kilowatt hour. If you have more irradiance, for example, almost double, then also price is almost half here. It's not really completely half, because if you have more irradiance, sure, the current goes up, as you know, but the temperature also goes up, and this reduces voltage, and therefore efficiency is a little bit decreased. And this, the blue area is then the competitiveness towards the diesel generators. So here diesel generator, here are they need about more than 15 cents per kilowatt hour to be competitive here, and that's we easily achieve if we stay, let's say, here for the sunny areas. We can even make photovoltaic power plants at the cost of almost €3 per watt peak in order to still be competitive against diesel. This now went a lot down, so this is a price of $130 per barrel. Now this is significantly down, but even if you take this one here, this crude oil in during that time, if you calculate the processing, but this was, if you take this as a reference, you still be competitive in sunny areas for installations costs or system costs below €2 per watt peak. From 2019, okay, this was here $69 per barrel. Diesel during that time has been $82 per liter, and then diesel worldwide is about $1 per liter. So yes, for new markets, what photovoltaic has the advantage, you don't have to create naturally a power plant to do that. You can also use it as a building material, so you can save for money, especially balance of systems costs, BOS costs, by substituting building materials, for example roofs, facades, and so on. And so this is a more and more important role. Therefore, this is an older example from the 90s in Berlin. So this is a facade. They even chose this color of the solar cells to fit to the facade. Here 17 kilowatt. This is also an additional advantage, because here you can see on the picture, but there's a river here, and the river reflects irradiance here and causes some albedo irradiance on the facade, and then the power production was more than expected. This is southern, I think in Saxony here, for example, also nice integration of the roof. Here also the photovoltaics serve as shading here for these office rooms, so they have to use less air conditioning because the sun is not, especially if the sun is very high at midday, so the shading is more, and therefore temperatures stay cooler in the office, and therefore you need less energy for air conditioning, plus you generate electricity by those photovoltaic panels. Here's another example here, the solar roof Herne, it's about 1 megawatt here. They even used selective lightning here, so they have put in some areas, they put photovoltaic panels at a different density, so there were solar panels with a low density and of solar cells, and here you have a high density of solar cells, and so they were able to control the lights. So this was set up by a computer program to have a really balanced irradiance illumination here in that hall. So you don't need any artificial lighting, and it's very, very pleasant for the eye because there's no bright sunshine coming in, but on the other hand it's still very bright. This during that time it was the largest photovoltaic roof at that time of 1 megawatt with an area covered of 10,000 square meters. Also you can think about other normal homes, facades and so on, because they got really cheap. If you see square meter price in the vicinity of about 100, even less than 100 euros, sometimes even 50 euro. So it comes into the vicinity of costs of facades and so on. Also for cars, especially if you think about electric cars. Fortunately, there's only one company, the Sion, which considers that as an option. So they cover the whole car with solar cells, and according to their data sheet, they are able to supply enough electricity per day to cover 34 kilometers of traveling by the electric car. So this is also a good idea if you don't use a car very often, every 2 days only, and so you don't have to think about a plug. You can always use sunlight for powering your vehicle. Also here's some more futuristic application where you can put photovoltaics and so on. I wanted to show you some links here at the end of the lecture, so you find it on our website of the University of Paderborn. So this is ai.uni-paderborn.de, or you just type in EET NEK, so this is our chair here, and you find, or my name, and then you find that website, as it's called Actual Grid Data. There you see the different websites where you can take a look on the actual energy production, on the prices, on the CO2 and so on. Try to show you now one data here. I hope it works. This is, hope you can see that here. So here you can see the electricity data from, this is actually today then, just 18th of May, so when I made this lecture. So you have here, can hover with your mouse over the different energy sources on the different dates and time. So you see here and at 12 o'clock at 17th of May, power production by photovoltaics was 32 gigawatts. And you see the consumption have been 60 gigawatts only, so more than half has been supplied by photovoltaics. This is here also wind, 9 gigawatts. If you come to all together, we have an overproduction. As I told you, the conventional power plants are sometimes unable to throttle down, and so there was overproduction, and this led probably negative prices. Here you see, because there's a very large share of renewables, that the CO2 emission factor, or the CO2 emission, the specific CO2 emission is very low. So it was 153 grams per kilowatt only during that midday, 17th of May 2020. While if in the nighttime, when you don't have a lot of wind and solar power, or for example here, what is this about 10 p.m. Here the CO2 emission factor was significantly higher. So you can also take a look at the power imports, exports. You see how much is exported. You see here where is it exported to Austria. As I mentioned, they have a lot of storage there due to the hydropower plants and pumped hydropower plants. And here in nighttime was something imported, not very much, from France. Here 1 gigawatt and so on. So you can look up the different import and export. The prices here, as you see here, I think this is the price here we mentioned here at 21 o'clock at 10 p.m. Was quite high, 26.5 euro per kilowatt hour. Not really high, it's just 2.6 euro cent per kilowatt hour. But the day I mentioned where we had a lot of solar and wind power here, the 17th of May at about midday, or around midday here, lowest price has been reached at 2 p.m. with a price of minus 16.76 euro. You can also click on overview so you have all the graphs together and take a look at it. Here's a link here. This is our university. You have the if you have the PDF file of that lecture, you can even click on the PDF link here, and then you can immediately access it. Okay, that was the lecture. I just give you some hints for the exercise. So the first part, as I've been mentioning, is to calculate the median annual growth rate in percent, small p, PV, of global installed capacity. If global capacity was 105 gigawatts, so it's quite a long time ago, 2012, and from 2018 it was half a terawatt, 509.3 gigawatts. So you have to calculate the growth rate. This is the gray part, theory behind it, and that is the final value and the initial value, and this is the growth rate which you should calculate. One task here. Yes. So you have here the according graph to that. So you presented that in the lecture. Then the next part of the question: calculate the year when the global energy demand can be fulfilled by photovoltaics, not only the electricity but even the energy demand. I think 18 terawatts, I think we gave in the very first lecture when we discussed about the potential of solar energy, also gave this number of 18 terawatts which we need to cover all energy by photovoltaics. And I shouldn't give you that, is 31.1% per year, and then you should calculate that. So I don't give you the solution for that. So what will be yes, the year and also the cost for that, including the cost regression, what you found out if you have a doubling of the installed capacity, you will have a certain reduction of prices, and this you should consider in order to calculate the final prices of the 18 terawatts. So how much is the negative growth in prices? You know this graph, you can calculate it from there. So it's okay, it's already given there, minus 24%, a doubling of installed capacity. So you have to know how much, how often you have to double it to reach the desired 18 terawatts. And so I don't give you the solution, you should do at home here. Yes, this was also some... yes, so you have to use some arithmetic numbers. Sometimes in your calculator you don't have all logarithm base. You should only have some specific base for the logarithms, but you can easily convert. For example, if your calculator, pocket calculator, only a logarithm of 10 or e, you can calculate it easy by dividing it here accordingly to reach the base b. For example, here b is 10, and then you have here, you can use both 10 and then, but you should then take the logarithm to the base of 10 of b, and then you have the logarithm to the base b of x. So this should be mentioned if you want to calculate that. It's a cost reduction and so on. So end price in 2018 was 30 euro cent per watt peak and so on. Please calculate it at home. Then the part 3 of the exercise, we now consider a solar carport. So we consider that it will be used for 15,000 kilometers a year, and it should be supplied by a PV systems. The car consumes 14 kilowatt hour of electricity per 100 kilometer, and the charging and discharging round trip battery efficiency is 90%. So what is the daily electricity to be supplied? Quite easy one. And yes, you should also calculate then the P generator. So I give you also the irradiance number for while the solar carports are not inclined very much. I give you also this number for 10 degrees of elevation angles, and so here we have the global irradiance on a tilt angle plane, like is given here on the solar carport, and this is 1032 kilowatt hour per square meter per year. So you have the optimal here, so you have winter and summer also here given. Performance ratio is 0.85. The nominal PV conversion efficiency at standard test conditions should be 17%, so we'd be actually a little bit lower due to that performance ratio. And these are the different months of the year and the production, and some mentioned at the rule over the thumb calculation that you take the irradiance, a typical day at the worst month of the year. And this is now for a tilt of 30 degrees. Elevation of 30 degrees, and this is for 10. So you see here that the distribution changes a bit. So here, especially in winter, the irradiance is significantly higher. cheaper, but okay, it's expensive battery and lasts long. If you would have cheaper battery, probably you would have only 2,000 to 3,000 full cycles only. And the question is here, how much is the size cost of that battery, considering the maximum depth of discharge, which is different from the lead acid battery, not 50% only, but 90%, and considering 2 days of reserve power. Calculate the electricity costs with battery place costs of for 100 kilometer driving of the indirect charge options, because usually in Germany you take the costs per 100 kilometer, therefore we want to use that also. And you want to calculate the indirect charge costs. So if you have PV costs 0.5 euro per watt peak, and mounting costs are 0.5 euro per watt peak for the elevation angle of 10 degrees, and for the next example of 60 degrees, so you get more cheaper solar electricity, but you have to pay more for the mounting costs, which is 70 cents per watt peak instead of 50 cents per watt peak. For comparison, to give you an idea, gasoline car at 6 liters of gasoline per 100 kilometer at 1.6 euro per liter is about 9.6 euro per 100 kilometer of cost. So you can compare your car to that, or the battery at least. I don't guess it's the consumption of the second battery and the PV investment costs. Then you have other options. You don't use a second battery, but you charge your car from the grid at night time, which is rather expensive. In Germany now for the final customers is about 30 cents per kilowatt hour, and here the 0.3 euro per kilowatt hour. And so we have a surplus in summer, and we can feed that surplus into the grid, but we only get 10 cents per kilowatt hour, 0.1 euro per kilowatt hour for that surplus in electricity. Then you should also make a calculations how profitable that is with the same site conditions. So you have costs of 0.5 euro for solar modules in a lifetime of 25 years, mounting costs of 0.5 euro per watt peak for the elevation angle of 10 degrees, and accordingly for an elevation angle of 60 degrees with 70 cents of installation costs. Yeah, mounting costs surrounding us 70 cents per kilo per watt peak. Oh, this is already the solutions I don't want to give you yet. This you have to do at home, so I don't want to. I go very quickly over it. So you can go. So you just do the calculation, and yes, good luck. And as I told, there's a public holiday called Pfingsten Monday, so you have some time to take a look at that lecture, which is a bit more extensive, and also at the more extensive exercise. Thank you very much.